All right, we're ahead of the game. We've already entered a C++ program or two. Parts of a C++ program. Generally, we will have more than one include statement. We'll have one or more include statements. This is what's known as a preprocessor directive. There are other commands besides #include, #include. We'll talk about those as well. Right now, this is the biggie. What this does is it brings in a library that we can then use in order to be able to use cout and cin. Then there's this line, using namespace std. Which namespace to use? Well, we don't know what a namespace is. Why don't we just throw a whole bunch of words at us? But I will demonstrate what happens if you remove that line. Now, every line of code in C++ has to be within a function, as opposed to Python, where we could just, willy-nilly, the first line of your program could be a command, a print statement or whatever. Instead, we have to put all of our code in a function, and we have to have a main function in our code, or else the compiler doesn't know what to hook up so that when the program is executed, it knows where to start. So every program you write, whether you even see it or not, is going to have a main in it. And what do I mean by whether you see it or not? There are development frameworks you can use where you pop open a editor and then you drag windows and forms and buttons around, and then you don't see the main function in there. Instead, the main function was generated by the editor. But it's still in there somewhere. And for the most part, we're always going to see it. That's where we're going to put our code. And we put our code in the main function between the braces. Every block of code is defined by braces. Most statements are terminated by semicolons. The exception is that if there's a curly brace, you never put a semicolon on the line above it. That would be wrong, putting a semicolon there. Not that you can see what I've done there, right? But, if we, can we get that out of the way? Yeah. So, that would be wrong. It would not compile. So never put a semicolon on a line that's followed by a curly brace. That's generally your rule of thumb. You also do not put semicolons on lines that begin with a hash symbol. Those are preprocessor commands. That's not even the C language. It's a different language, which is used on top of C in order to manipulate the files. So we have special characters. Pretty sure we've already used some of these. The double slash is the beginning of a comment. There are other kinds of comments. There are multi-line comments. A single-line comment, you use // just like in Python, we use the $. But then you have at one time, this was the only style of comment that the C programming language supported. Then it was extended to support single-line comments. Why? Because it was kind of annoying to have to do this. This is a single-line comment like that, right? Cooler just to do that. So they added that. Now, one thing you will see out in the wild is that people will do this just to make their code look fancy. Why does that work? Because it's got that. That opens the multi-line comment. And it's got that. That closes the multi-line comment. The fact that it's got all this other stuff in here is, it ignores that. It just accepts it, that everything between that and that is part of the comment. So you'll see that. And they don't have to be marked out with asterisks. Sometimes you'll see people do whatever. And people can spend an inordinate amount of time making their code look fancy. You can do that. Another thing you'll see is like this. Whatever. You'll see those things. You'll pick some style that you're fond of. or you'll go to work someplace where, the other programmers have settled upon a style and you'll probably adopt it. So that's a comment. Pound sign, or as the British call it, octothorpe. Most ridiculous symbol name ever, octothorpe. Octo meaning 8. Doesn't have 8 lines in it. I'm not sure how they came up with that term. Pound sign is the beginning of a preprocessor directive. And then we have I call them angle braces or angle brackets. Open and close brackets. Enclose the file name in the include. They also just mean less than or greater than in other syntaxes. But in the one that we see here, they enclose the file name. Sometimes in your include statement you will use double quotes. I'll explain when you use that. Until then, always use the angles. Open and close parentheses. You use those when naming a function or when calling a function or when you want to group things together in a mathematical expression. Open and close curly braces. Defines a block. In other words, a group of statements. Open and close question marks. That's a string. Single quotes mean a single character. Double quotes declares a string. And then the semicolon is the end of a programming statement. So cout. You use what's known as the stream insertion operator. In other words, less than, to send output to cout. Programming is fun. So, cout. Hello. And then they end it there. And then they have another pair of arrows there. So when that runs, it's going to print hello there. Why is it going to put a space there? Because there's a space there. If you took that out, it would print hello there. Here they put it on a single line. Here they broke it into 2. This still worked. This would not print hello there on 2 different lines, like you might be expecting from Python. Remember, your print statement usually went to the next line. Since it did not see an end of line marker, it just kept printing like that. So if you had 20 couts in a row without an end of line marker, all that stuff would be concatenated, would be all put on the same line. So programming is fun. It's going to say this. Programming is fun, just like that. Now it's going to leave the cursor there. What if you didn't want to leave the cursor there? What if you wanted it there for the next thing to happen? Well, there's 2 ways to do that. One is you can use \n. Not /, not the one under the question mark, but the \, the one near the enter key, above the enter key. Underneath the, well, anyways, you know where to find it. If you have that, it will skip to the next line. Or, in this language, you can send an ENDL, and that's an L, not a 1. So if I use that in class, and you're typing along with me, don't type END1, type ENDL. If you did this, programming \n is fun, then what you would see is programming, and then on the next line is fun, because this caused it to go to the next line. And then this would cause it to go to the next line there, and it would be ready to display the next thing. So you can use the ENDL manipulator. I like us throwing in a random word. Manipulator, that thing, to start a new line of output. So this will produce 2 lines of output. Programming is, go to the next line, fun. You're usually going to put that after every cout statement. At least every cout statement, that's supposed to be its own line of output. Right? Programming is, hit enter, fun, hit enter. You do not put quotes around ENDL. If you really felt obsessed with putting quotes around it, you'd put quote \n, end quote. The last character in ENDL is a lowercase l and not the number 1. Now one thing that you'll notice as I'm typing is I'll do something like this. Cout. The answer is India, right? And then I'll do ENDL. Or I'll do this. The program is done, \n. I could have used ENDL here, right? I'm going to put the alternate, the variance. I could have put quote \n quote there, or I could have taken that out and done ENDL there. I just try to go with what's faster. To me, typing that is easier than typing that. To me, tagging on a \n at the end of my string is easier than adding an arrow ENDL. So you can always use one, you can always use the other, or you can mix and match. It doesn't matter. The escape sequence, \n, means go to the new line. There are other escape sequences. \t is a tab. That's the other most common one, but there are others still. So the include directive inserts the contents of another file into the program. And I'm getting itchy for us to actually start typing in some C. So I'm going to go ahead and launch Visual Studio while we're looking at this. Like I said, it's not part of the C++ language. It's an addendum that the compiler uses. It's its own separate language, preprocessor commands. Once you get used to using them, you start kind of wishing that other languages supported it. The # include line is not seen by the compiler. It removes the preprocessor commands and modifies the file according to them. When you hit the run button or when you hit the build button, what happens is first the preprocessor runs and it manipulates all your files to follow the commands of the preprocessor. Then and only then does the compiler run, and it stitches all your source code together into machine language. And then something called the linker goes and it links together all your machine language files, your .obj files, which stands for object code, into a standalone executable. You do not place a semicolon at the end of the # include file because it's not a C++ command. So variables and literals. A variable, you declare like that. You have to declare it before you can use it, unlike Python. Let's make a few notes about variables. They have names, types, values, and a memory address. Specifically, these are the three that we care about at this point. We can get the memory address of the variable as well, unlike in Python and Java, where you really can't get a hold of that memory address. The C++ comes from a lower level beast of a language, C, where you do care a lot about memory addresses and you pass them around. So, yes, you can get the memory address, and you can store it in what's known as a pointer, and then you can do stuff with that memory address, unlike in other languages. These are the components of a variable. The name, we know what it is, like Fred, Barney, temperature, height, length, width, area, any of those things. File name. The type is what data can be stored in it. Int, float, double, string. Those are all variable types. Values. Well, once you've declared your variable, the reason you declared it to begin with is so that it can contain some kind of data. Right? So you could put a 1 in it if it was an int, or if it's a floating point number, you could store 3.14. Or if it's a double, you could store an astronomically large floating point number in it. Or if it's a string, you could store a file name, or somebody's first and last name, or the state that they live in, or whatever. And then the memory address is just where in the computer's memory that variable is stored. That's a slight simplification, but that's how to think about it. So I'm going to do File, New Project. I'm going to make a Lecture C console application. And I accidentally made a C# one, which was not my goal. So I'm going to close that solution and make another one. I'm going to call it C2. You don't need to do that because you didn't make the same mistake I did. Lecture C2. It needs to be a C++ application. Empty project. I'm going to wind up putting boilerplate in it. So I have saved my boilerplate out on the desktop. I'm going to go grab it to save myself time. So what do I do next? Right click on source files, do add new item, and it's going to be a C++ file, .cpp. Click add, paste. All right, now my boilerplate's there and I'm ready to go. If you don't have boilerplate made yet, I strongly recommend you do that, because otherwise you have to type it every single time. Okay, so we could declare some variables. Int length, comma, width. Maybe another one to hold area. Int area. I could have declared them all in the same line. I have to declare those variables before I can use them, unlike Python. You can assign values to them as you declare them. That's what's known as initialization. I could say length equals 0, width equals 0, area is equal to 0. Now in this case I didn't bother. I wouldn't have bothered normally, because those variables, those values are going to be assigned, and so those initial values will be ignored. But I'm going to leave them there anyways, just as a demonstration. So I'm going to write a little program that will calculate the area of a rectangle. Those who just sat through my Java class already know what this is going to look like. I'm going to display a message. What is the length? Then I'm going to read in that variable. Then what is the width? And then I'm going to read that in. And then I'm going to do a calculation. Area is equal to length times width, and I'm going to display the output. So I'm going to use CIN to get the input. I'm going to use cout. Cout stands for console out to display. So cout, what is the length? Question mark, space, end quote, semicolon. Now CIN, arrow, arrow, length. And by arrow, arrow, I mean greater than, greater than. Angle brace, angle brace. I'm going to do the same thing for width. Cout, less than, less than. What is the width? CIN, okay, what is the width? Question mark, space, end quote, semicolon. CIN greater than, width, semicolon. Now I've gotten my input. I'm going to do the calculation. Area is equal to length times width. Now I'm going to display the output. Cout, the area is space, end quote, and then another pair of braces, angle braces, less than, the area variable, and then less than, ENDL, not END1. All right, after I've made sure this works, I'm going to remove the white space between it, most likely. But for now, I'm going to leave it like that. And I'm going to rebuild it and make sure it works. Build, rebuild solution. Rebuild all started. It all succeeded, so I don't have any errors in my error list. Maybe you do. I'm going to run it and test it. All right, what is the length? 20. What is the width? 33. The area is 660. So that worked. Notice that in this language, unlike Java, unlike Python, the same syntax figures out whether it's reading into an int or not. We didn't have to do anything special. We didn't have to call next int like we did in Java. We didn't have to use the int function, in order to turn it into an int. C++ just does that automatically with the CIN arrow arrow. I am sorry, I need to take about a minute break. I will be right back, then I'll help with syntax errors. So if you didn't get the # include in your IO, # include IO stream, then you're going to get errors on things like cout and CIN. Now that we're here, I am going to mention what this using namespace std does. When you bring in something from a library like that, if it's something that Microsoft has provided, and not just Microsoft, if it's part of the C++ standard libraries, the functions will be enclosed in namespaces. What that exactly means, we will learn later. But for now, if I remove that, the program is no longer going to work, and the reason why is our couts and our cins no longer work. That doesn't mean that they're not available to us, though. It just means that without this using namespace std, it doesn't know where these are. But if I go in and I make that std : cout and std : cin, that fixes that. Now I have other ones down, I would have to fix them all. And I don't think I'm going to bother to do that, but I would have to hit std : std : std : So what using namespace is it's like if you said, I live on 123 Main Street. Well, if you were telling that to somebody on the internet, they wouldn't know what city you were in, right? But if you said, I live in 123 Main Street in Tulsa, then they know. Well, this is saying that this is part of the namespace. That's where it's supposed to find the cout function. But you can tell it to assume that. You can say, I don't feel like typing std in front of everything that requires it. So it'd be like saying, all right, every address I use from now on is going to assume that it's part of Tulsa. I live in Tulsa, and my address is 123 South Main, right? And my brother's address is 456 South Eastwood. That kind of thing. We'll see how to set up a namespace. But for now, just kind of accept it. Also, I will mention periodically that it's considered poor form to use this, using namespace std. However, it's what the book does. In code on the internet, you will see people not use that line, and then they will go ahead and have std : throughout it. Just accept for now that the book has us doing it. I'm going to do it in here because it makes the code easier to type. But if you go to some job with other C++ programmers, then they may strongly tell you not to do that. And there are reasons why. I did start the recorder again, did I not? Okay, so here's a variable definition. We need a variable called number. It's stored in an int. There's all sorts of different types of variables. There are, whole numbers, integers. There are floating point numbers, like floats and doubles. Variables are distinguished both by their type and by how many bits are dedicated to hold them. A bit is a single on-off value, and a byte is a cluster of 8 bits. And a 16-bit number can hold more than an 8-bit number. And a 32-bit number can hold more than a 16-bit number. And a 64 one can hold a much larger value still. And so you have all sorts of different types of ints you can play with. And you have several different types of floats you can play with. And as well as specifying how many bits it can support, you can support whether you want, you can pick whether you want it to allow negative numbers or not. If a number is unsigned, it means that it's positive only, that no negative numbers are allowed. And the advantage of that is that, for reasons we'll explain later, it can hold twice as large a number. The maximum value that can be stored into an int is a little more than 2 billion. But if it was an unsigned int, if I added the word unsigned in it, meaning that it can't go negative, then the maximum value in it would be 4 billion. And we'll talk about why when we start talking about the ones and the zeros in the binary format of numeric data. So a literal is a value that is written into the program's code. It's literally included in the code. It's not something the user types in, it's something right there in the code. We have 2 literals here. This 5 is a literal, and this 0 is a literal. Those are numeric literals. And then we have what's known as a string literal. Everything between the quotes is a string literal. The user can't change that stuff, unless they get a hold of the source code. So literal is a fancy word just meaning something that is typed into the source code, representing a numeric value or a string value. You can have integer literals and you can have floating point literals. Floating point literals have a decimal point. Integer variables do not. Going back to our code, I want to illustrate something. If I run it and I type in something with a decimal point, like 1.5, it goofs up. I only hit, run it yourself just to witness what it's doing. What is the length? 1.5. Hit enter just once. And then what is the width? The area is 0. But it's really not what I wanted it to do. It messed up. When I typed in 1.5, since this variable was only supposed to be an int, then it messed the input up. If we want to correct that, if we want to allow fractional values with decimal points, we need to change the data type. Now, the good thing is that it didn't blow up, as opposed to Python, where if you use the int function to turn a string into an integer, but then you gave it a value with a decimal point, Python will crash unless you use some kind of exception handling. And Java will as well. If you use nextInt to read in an integer, but then you type in a floating point value, Java will generate an exception. C++ doesn't, but it doesn't behave correctly. So I'm going to change these ints to floats. Float length is equal to 0, width equals 0, and then float area is equal to 0. That way, when I run it, I can type in a fractional amount, and it won't blow up, or it won't go nuts like it did. 1.5, and then what is the width? 2.1. The area is 4.65. Identifiers. Our variables are identifiers. However, function names are also identifiers. They identify the function name. And when we learn about classes, class names are identifiers. And class members, like methods, which is a function that's part of a class, are also identifiers. It's just a fancy term for variable name, or class name, or function name. And there are some rules for what you can call your variables. The rules are the same as they are in Python. You can use letters, you can use digits, but they can't start with a digit. So identifiers, I think I misspelled that, equals variable names, function names, class names, method names. That's probably about enough. So the rules for identifiers, including variable names, you can use letters and digits. Cannot start with a digit. As far as special symbols go, you can use underscores. You're not supposed to be able to use dollar signs. However, Microsoft allows you to use dollar signs, but people would think you were very strange if you use dollar signs in your variable names. Like if I did this. String name dollar sign. Name or first dollar sign name. That's valid syntax on a Microsoft compiler. It would not be valid syntax in other compilers. It's a non-standard thing. And it just looks crazy anyways. So you're not going to use it. However, you would probably use underscores. That is one naming convention. Naming conventions are just kind of rules of thumb that you can follow to try to make your code easier to read. Something like this, string space first underscore name, and then string last underscore name. Is that the only way you can do it? No. Well, for one thing, you could just call it like fn and ln. But the shorter the variable name, the more terse the variable name is, the harder it is to read the code. You should try to write your code in a way that's easy. And another way you could do it is that, first name, last name. This is a very popular way in Java. And maybe C++ programmers are wandering into that territory as well. Back when I first learned it, people used underscores. This is known as camel case because it's got a capital hump in the middle of it. I've already mentioned that in another lecture. So keywords. This language has more keywords than we know what to do with. A whole bunch of keywords. Keywords are the syntax of the language. They are the things that define the language. We cannot use these as our own identifiers. We cannot create a function called long. We cannot create a variable called static. Do you have to memorize all these? No. By the time you're done with this course, you'll recognize probably half of them, maybe more. Quite a few of them we will not hit, though. A variable name should represent the purpose of the variable. Items ordered, that's very clear. If you just call it I or IO, that's not clear. The purpose of the variable is to hold the number of items ordered. We can tell that from its name, and that's a good thing. So, the first character can be a letter, it can be a digit, or it can be an underscore. After the first character, you can use the alphabetic characters, numbers, or underscore characters anyway. This is just saying that you can't use a digit. And upper and lowercase characters are distinct. You can, use mixed case and they mean different things. If you do this, M is equal to 3, then later on you cannot print out capital M. That's the same as Python. That's the same as in any other modern programming language. There was at least one programming language in the 60s where if you typed in something in lowercase, it meant it was a command for the computer, and if you typed it in uppercase, it meant that it was data, instead of putting quotes around it. Well, that's an odd idea. Anyways, so it is a case-sensitive language, so you can't do this if x is equal to 3. That's how we type things in English. You capitalize the first letter, but you didn't capitalize your first letters in Python, Java. You're not going to do it in C++. So valid and invalid identifiers. I'm going to scroll this over here so that we can't see the answers. If you've already memorized them, no fair. Is that one valid or invalid?
Valid.
Yeah, that one's valid. How about that one? It's also valid because underscores are legal. Spaces are not. So if it was total space sales, that would be invalid. How about that one? That one is kind of tricky if you've done other programming and object-oriented programming languages. But as an identifier, you could not say total.sales. Fourth quarter sales, is that one valid or not?
No.
No. And this one would be valid in Microsoft, but not in other implementations of C++. If we scroll this over, it's going to say that it's invalid. I'm not going to ask you whether dollar signs are acceptable or not, because that would be a trick question. So integer data types. As I mentioned, there's all sorts of integer data types. Way more than in other languages. We've got short, well, I shouldn't say that. Python, for example, does not distinguish between ints and short ints. What is a short int? It's something that in the current specifications for C++ is 2 bytes long. At least 2 bytes long. An unsigned short int also occupies 2 bytes. An int occupies 4 bytes. An unsigned int also occupies 4 bytes. A long int, and this is where Microsoft is crazy. Every other compiler on the planet says that a long is 8 bytes. Microsoft instead says that to get 8 bytes for an integer type, you have to use long. And so periodically I will say long, and it sounds silly, like the name of a panda, but that's how you declare an 8-byte integer in this language. Whereas in Java, you would just use the word long. And then there's the unsigned long int. And we're using 4 words here to declare a data type. Honestly, you can leave the word int off. You can just say short, and it assumes int after that. long. You can just use long, and it will assume that it's followed by the word int if you leave it off. Now, where these typical ranges come from? Now, I've just lectured for 2 days to the Java class about bits and bytes, and I'm not ready to do that again for y'all. We're going to get to it next week. Just know that the more bytes that is dedicated to a piece of data, the larger the magnitude of it. Just like you had an 8-bit Nintendo, which could display up to 256 colors on the screen, and then you bought your 16-bit Genesis or your 16-bit Super Nintendo, and it could display 65,000 colors on the screen at the same time. And then you bought your 32-bit PC, and the 32 bits also controlled the memory address, so it could hold like up to 8 gigabytes of RAM. And then Windows came out with a 64-bit version, and so computers started supporting 64-bit architecture, which can hold astronomically more than 8 gigabytes. It's limited by the hardware, it's not limited by the operating system. So the more bytes, larger the value. So a short can hold the maximum value of 32,000. If it's unsigned, it can hold twice as much as I mentioned. An int can hold up to 2 billion. If it's unsigned, it can hold twice as much as that, but it can't go negative. A long can hold up to whatever that is, 9 super zillion. And an unsigned long can hold twice as much as that. And these are all floating point types. And there are other floating point types still, but you're kind of shoehorning something else into being treated as an int. And that's specifically the character data type, CHAR, which you typically use to hold a character, not a number. But you can store a number in it. So here we've decided that you have a checking account and your checking balance can go negative. So you're going to make it an int. And here you've decided that you're going to record the number of miles traveled and your miles can never go negative. So you're going to make that unsigned. And then I guess we've decided that days can be negative as well as positive. You know, I am negative 3 days old, whatever. So we're going to store it in a long. Now in this language, in Microsoft, there's no difference between an int and a long. If you're using a Linux compiler, a Mac compiler, like GCC for the Linux fans, I believe that's also what is used on the Mac, then a long holds a much larger value. As mentioned in the previous slide, the maximum value of an int is about 2 billion. So we could only hold 2 billion in our checking account. If we're Elon Musk or Bill Gates, then that would not be adequate. We would need to have a larger variable dedicated to our checking account.
So those longs are floating points? But
No, these are still all integer types. Everything on this page is an integer type.
Oh, I thought you said. I don't know why.
There are floating point types, but the big version of a float is called a double.
Okay.
Yeah, so you can get long floats, but you instead put double.
Okay.
Very good question. What does the fact that it's an integer mean? It means that it cannot store a fractional part and it cannot use an exponent. You can't say 3e to the 79 and have it be stored in an int. I say that. It's possible it would compile correctly. C++ is a little bit more generous than Java in that respect. It will do some conversions automatically that Java disallows. And I'm not going to talk too much about Java, but there's like 3 students in here who are taking both classes at the same time, and so I try to distinguish them when I hit something like that. Integer literals. This is a literal, literally typed in the code, and we're storing it in a variable. Why are we storing it in a variable? Probably because at some point it's going to change. At a certain point, somebody's going to make another order, and items ordered will change, from 15 to 16. Otherwise, you just use 15 throughout. However, typically when you use literals, you don't want to sprinkle them throughout your code. They're called magic numbers in that case. Like if the tax rate, and you encode the tax rate as 8.75. Well, what if the tax rate changes? What if you used 8.75 in 70 different lines and spread amongst 4 different C files. And then the tax rate changes, and so you have to go and you have to modify each one. And then you decide to write this program so that your friends in Tulsa can use it, and they have a different tax rate. And you've got to write a different version for them, or whatever. Instead, you typically want to store your values in variables. You can store them in constants if there's something that are not going to change while the program is running. Typically you want to avoid magic numbers. Magic numbers are things that appear in the middle of your code. They're literals that may need to change in the future. And the speed of light is probably not going to change, but it certainly is easier to type in speed, or SOL, speed of light, or C, the physical term for the speed of light, than it is to type in 3 point, or whatever it is, 6.022, exponent to the whatever. So integer literals are stored in memory as ints by default, but if you want, you can make them a long. The only time you need to do that is if the number is too large to be an int. I'm going to go in here and make a long, BG salary, Bill Gates salary. And it's equal to, he earns a lot, he earns more than $2 billion a year. He earns 999. Have we gotten past 2 billion there? That's, yeah, I think we have. Or that's 999 million, so I'm going to tack on 3 more nines. So that's 999 billion right there. I'm going to rewrite that. 987654321. That number is too large to be stored in an int. But I've got a long here. That ought to hold it, and yes it will. But the problem is that by default, integer literals are assumed to be of type int. That's going to actually be a syntax error. No, it's not. What do you know? There again, C++ is being more generous than it should. I should have to suffix that with an L to say this is longer than an int, and that's okay. If I leave that off and then I C out BG salary, this is just my experiment, NDL, is it going to print that whole number? Let's find out. Yeah, sure did. Okay. So why do we need that L suffix? Don't know. How big can we make this? Do we get to a point where it declares a syntax here? No? Alright. The L suffix is useless in the Microsoft language. Microsoft's compiler is not standard, and they've made a lot of strides towards making it standard. However, in this classroom, we have Visual Studio, 2013 installed or something like that. And so any progress past then is not reflected in the compiler that we're using. Just know that if you tack an L onto it, it turns that int into a long, and that in a lot of environments you have to do that if the literal you're typing is too large to be stored into an int. And you Java guys would have to do that. To store an integer constant in long, you could put LL. We've already seen it's not necessary. If you want to use base 8, which we never will, you prefix it with a 0. If you want to represent a hexadecimal number, you prefix it with 0x. Have we talked about hexadecimal yet? I don't think so. But if we wanted to, we could say that BG salary is equal to OX345FF. Now that looks silly. You don't know what it's doing. But this is just a hexadecimal value. Hexadecimal is a counting system where you have 16 different digits rather than just 10. Decimal has 10. And we'll lecture about that at another point in time. But if you ever see a number prefixed with 0x, that's what it means. All right, the char data type. The char data type holds a single letter, unless you throw some compiler switches, which tells it to support 16-bit characters. This is an 8-bit character. It can hold any ASCII value. An ASCII value is one that you can find on the ASCII data chart. That's another upcoming lecture. Anyways, it can hold a single letter. You have to declare in single quotes rather than double quotes. If you do this, the compiler is going to flag that as an error, even a Microsoft compiler, because double quotes are used to hold strings. Single quotes are used to use characters, and you can't mix them. You can't mix and match them, unlike Python. So, if you are going to get and process a single letter, you would need to declare that variable as being of type char or char, and then that dedicates 1 byte for holding that value. Character literals must be enclosed in single quotes, like that, apostrophes. And I'm sorry this is such a lecture-heavy lecture. Don't go to sleep. All right, so a string. A string is represented as a literal within double quotes. Now, inside the computer's memory, it knows when the string ends because the next byte after this series is what's known as a null. It's actually a 0. Null and 0 are the same thing. If you print out the value of null, you'll see a 0. Now, let's see if that's true. I'm going to go here, back to my code, and see out a null, just to see what it prints out. Oh, what do you know? It didn't know what a null was. Null. All right, 0. The point of the slide, whoops, is that every string is what's really known as a character array. An array is a sequence of values stored contiguously in memory. Each element of the string is a single character, and the way that the computer knows where the string ends is with the null. So when you say string is equal to hello, quote, end quote, and then you needed to know how much memory that was occupying, it's not just occupying 5 characters for the HELLO. It's occupying a 6th character to hold that null. The C++ string class. It's a special data type that supports working with strings. Makes it easier, makes it far easier to do input and output and manipulation of strings. To get it, you have to include the library, # include string. Then you can declare string variables, like first name and last name. And they can receive string literals with the assignment operator. The assignment operator is a fancy term for the equal sign. When you're assigning things, you use a single equal. When you're comparing things, you use a double equal. That's just like Python and Java. And you can display a string just like you can an int or a long or a double or a float with cout. You can read an input into a string with the other arrows, a string insertion operator. CIN, arrow, arrow. Floating point data types. The floating point data types are float, double, and long double. And when you asked if a long was a legal data type or not, and I said no, I forgot that it was. Let's see if it differs from a double. It does not. That's why I forgot about it.
You have a long double?
Let's find out. Nope. Okay. So really, you have a float and a double. Just use those. And a float can hold between 3.4 to the -38, a very small number, a point followed by 37 zeros followed by a digit, or 3.4 to the +38, which is a 3 followed by 38 zeros. So ints, basically used for numbers less than 2 billion. Otherwise, use long longs. Floats, you use for exponents up to the 34. much larger. Exponents up to the 340, I believe. No, 308. Now something with 34 zeros is a pretty long number. But if you ever need more, you have the type double. But the float and the double not only determine the size of the exponent, they determine the size of the mantissa that precedes it. The mantissa is a number before the exponent. If it's a float, you have about 7 to 8 digits of accuracy in the mantissa. So like, that's about as far as it could go. 1, 2, 3, 4, 5, 6, 7, 8. If it's a double, it could get much more precise. It could go out to 16, 15, 14, 15, 16 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4. That would fit comfortably in a double. Anyways, I'm not going to max out the exponent. Anyways, and this would not fit in a float because I said that the largest exponent was a 34, so that was dumb. I'm going to make that 18, something like that. This would fit in a float. This would fit in a double. If you assign this number into a float, it might not give you a syntax error, but it's going to lose some data. That is as precise as it can get. So if you try to put something with more decimal points, with more digits of precision in it, they will get lost. And if the exponent is too large, that's a very serious problem. We can play with that. Let's go to our code. Let's declare an int called I. Let's declare a long called LL. Let's store a really big number in the long. LL is equal to 987654321, something that's 10 digits long. And then let's turn around and stick that into an int. And let's print them both out. Cout LL, arrow space, end quote, arrow I, arrow ENDL. Here I'm shoehorning too much data. There's no way that that can possibly fit into an int. In Java, that would actually be a syntax error. You would have to correct it. This language might give you a warning about it, but it's not going to cause a syntax error. But what you get, check this out. The same value, what is that, 98 billion? Something like that, turns into this when it's stored into an int. What we got was known as data overflow. The data value was too large to be stored in the 4 bytes available to us to hold an int. You can easily get overflow by multiplying values, right? Even if a number is sitting there being held into an int successfully, what if you double it and you double it and you double it again? Let's write a loop that'll do that. That'll double something like 10 or 12 times. Not that we've written loops in this class yet, but you know what a loop is. So I'm going to set I equal to 0, and I'm going to go while, quote, I is less than 10. Feel free to type along or not, whichever one you want to do. And I need another int to play with, so I'm going to declare one right off the bat. X is equal to 0. No, X is equal to 1 because I'm going to double it each time. So I is equal to 0, X is equal to 1. So I'm going to write out the value of I. Now I'll write it out after I double it. X is equal to X times 2. We're going to double X each time. And I plus plus, we're going to add 1 to the value of I. You Python programmers are used to doing this. I plus equals 1. That works in this language, but this, although invalid Python syntax, is the preferred way of doing it in C++ and Java. Just means increment it, add 1 to it, and store it back into I. And let's print it out. Let's see out X followed by a space, in space, followed by I, followed by ENDL. Now when you double a number 10 times, it may get larger than 2 billion. I don't recall. We'll find out. Nope. We're going to have to double it a lot more than 10 times. So I'm going to make it double it 20 times. It still probably won't be enough to illustrate overflow. Nope. How about 30? We'll get there. Nope. 40. That'll do it. All right. Check it out. After doubling it 30 times, when it doubled it the 31st time, it was too large to fit in there because it was no longer less than about 2 billion. And so it flipped and went negative for reasons we'll talk about when we sit and talk about bits, bytes for a lecture. Specifically the sign bit, the first bit in a number, got set, and so it was treated as a negative number. And then it really went nuts. So you have to pick your data types carefully. If your number is going to get larger than 2 billion for whatever purposes, then you're going to want to declare it as a long if it's an integer type. Or you're going to want to declare it as a double if it's a floating point type. So floating point literals you can represent like that, or you can represent with the E for scientific notation. Specify the exponent, either positive or negative. You can force a numeric value to either be a float or a long double. You don't have to specify it to be a long double because it's a double by default. But if you want to insist that a number is a float, you put an F there. Again, that's important to your Java guys, not to your C++, I believe, because I believe if we put in a number that's too large to hold into a float, it's still going to accept it, not give us a compilation error. Let's prove that to be the case. Now, we don't even have to because by default it's being treated as a long. And it will do the conversion on the fly to store it in a float. The bool data type. Bool holds either true or false. You Python guys need to type in a capital F and a capital T. In C++ and Java, it's a lowercase f and a lowercase t. They are small integers. Well, that's vague. They're actually only 1 byte long. Now, a byte can hold up to 256 different values, so it may seem like that's overkill for holding a bool. But a byte is the minimum value that can be shuffled around in memory, pretty much. And so that's the smallest data type. And a char is another 1 byte data type. So false is represented by 0 and true is represented by 1. So for example, if you create a variable called bool, it's called all done, and you set it equal to true, then inside memory, it's got a 1 in it. If you print it out, probably would print a 1. Unless cout is smart enough to print true. Let's find out. Cout, arrow, arrow, true, arrow, arrow, MDL. Let's find out if that says 1 or true. 1. Okay. Boolean variables. Boolean variables are typically also known as flags. They indicate a state. This is not an example of that. But you could write some code that used a Boolean variable, like this. Let's declare something called temperature. We're going to set it equal to -13. And we're going to declare a bool called frozen if temperature is less than -13, then frozen equals true, else frozen equals false. Then later on we would use that for some purpose. If frozen, do something. So frozen is a flag. It indicates a state, a true-false state, which you would later check and do something based on the value. The flag term, the term flag probably predates the term bool. The C language in 1970 did not have a bool data type. In fact, it was only introduced in the 2000s, long after the C++ language in 1980 defined it. All right, so it's time to stop the lecture. We're most of the way through chapter 2. I wonder if we've learned enough in order to check another homework, to do another homework assignment. Let's go take a peek. So here's what the homework assignment's going to be. Download it and take a peek, and I'll upload it to our correct Dropbox. So our task, using the same techniques as we did in the last one. We're going to ask for weight in pounds and then display their weight in kilograms. I don't think we did that conversion. I give you the formula. Kilogram is equal to pounds divided by 2.02. Excuse me, 2.2. Now that's not precise. If you feel like looking it up and being more precise, you can do that, but it's a close approximation. And then some other tasks. Ask the user how many cows they have and display how many pigs they could trade for if one cow is worth 3.5 pigs. Task. Ask the user how much money they have and display how many hamburgers they can buy if each hamburger costs $2.99. The formula is burgers is equal to money divided by 2.99. Now you'll have to kind of decide whether you want to say I could buy 1.2 cows or whether I can buy 7.8 burgers. If you think it's cool to represent cows in fractional values or burgers in fractional values, declare them as being floats or doubles. If you don't think that's cool, declare them as being ints. And in task, ask the user for the radius of a circle and calculate the area and the circumference of the circle. Google the formulas or shoot me a message to ask. Area of a circle, I believe, is pi r squared. Circumference is 2 pi r. Easy to find by Googling. Just type in Google, area of circle, and it'll show you the formula. Now let's create a Dropbox for you to upload whatever you typed in, which probably is not much. I think the form of the lecture was abstract enough that a lot of people weren't typing in everything, and that's okay.